Okay, in this lecture we're going to cover our section 4.3 material on the method of undetermined coefficients for higher order non-homogeneous linear equations. So here we know to solve a non-homogeneous equation, our first step is to solve the corresponding homogeneous equation to obtain what we call a homogeneous solution. And then we add onto the homogeneous solution some particular solution of the non-homogeneous equation. And one way that we can find this particular solution for a non-homogeneous nth order linear equation is to use the method of undetermined coefficients. And we can make use of this method provided that the non-homogeneous term, g of t, that forcing function, is of an appropriate form. So just like we saw in chapter 3, when we talked about the method of undetermined coefficients for second-order equations, we need to determine the form of our particular solution. And the way that we determine the form is by looking at the form of g of t. And as long as g of t is either a polynomial, an exponential, or a sine or cosine function, or products or sums of those types of functions, then we can use this method of undetermined coefficients. And the way that it works is the exact same as what we saw in chapter 3. Once we know the form of our particular solution, we can determine our coefficients by substituting that particular solution into our non-homogeneous equation. So let's look at some examples of how this will work for higher order equations. In this first example, we are asked to find the general solution of this third order linear non-homogeneous equation with constant coefficients. So we know our first step to solve a non-homogeneous equation is to consider the homogeneous equation. Y triple prime plus y double prime plus y prime plus y is equal to 0. And to solve this, we could look for solutions of the form y equals e to the r times t power, which means that r has to satisfy the characteristic equation r cubed plus r squared plus r plus 1 is equal to 0. And I could factor this by first factoring out an r squared from the first two terms, which would leave me with an r plus 1. And then I have another r plus 1 for my last two terms. So if I factor out the common factor r plus 1, I'm left with r squared plus 1 is 0. So it follows that my roots are r equals negative 1 and plus or minus I. So for these roots, the general solution of the homogeneous equation, or homogeneous solution, would be c1 e to the negative t plus c2 cosine t plus c3 sine t. And now our next step is to determine some particular solution of the non-homogeneous equation. And to determine the form of this particular solution, we're going to look at the form of this g of t function on the right-hand side of our equation. And we see here that g of t is a constant times e to the negative t plus a first degree or linear polynomial. So let's look for a particular solution of that same form. Capital Y of t, we could take some constant times e to the negative t. But we see that since r equals -1 was a root of our characteristic equation, that a constant multiple of e to the negative t is already part of the homogeneous solution. So for our particular solution, that first term we would consider would be a constant times t, e to the negative t. And then the last part of our g of t function was a first degree polynomial. So we could consider some general first degree or linear polynomial, something of the form bt plus c. And now none of these terms are already part of the homogeneous solution, so this will be the correct form. And to solve for a, b, and c, we need to substitute into our non-homogeneous equation. And since this is third order, we're going to need to find our first three derivatives of this particular solution. So let's look at it. For capital Y prime, we have a times, by the product and chain rules, we get a 1 minus t e to the negative t plus b. Then for the second derivative, we have a times a -1 minus 1, and then plus t, all times e to the negative t. And then for the third derivative, y triple prime, we have a times, by the product and chain rules, we get a +1 plus 2, so 3, and then minus t e to the negative t. So let's take these expressions and substitute into our non-homogeneous equation and see what we have. So here we are looking for y triple prime plus y double prime plus y prime plus y, which has to equal our g of t function, e to the negative t plus 4t. So substituting in these expressions that we found, our third derivative is a times 3 minus t e to the negative t, plus our second derivative, which was a times -2 plus t e to the negative t, plus y prime, which was a times 1 minus t e to the negative t plus b, and then plus y, which was a t e to the negative t plus bt plus c, and this still needs to equal e to the negative t plus 4t. So let's see what we get when we collect like terms here. Let me start by grouping all of the terms involving t times e to the negative t. So summing these terms, I have a -a plus a minus a plus a times t e to the negative t. So all of these terms cancel one another. We're left with 0. And now let me look at the terms that are just constants times e to the negative t. So grouping these terms, we have 3a minus 2a plus a, which leaves us with 2a times e to the negative t. And then let me group all of my linear terms together. So here we have a b times t, and then a plus b plus c. So our coefficient of t is b, and then my constant coefficient was a b plus c. And this has to equal e to the negative t plus 4t. So equating these coefficients, we find that 2a has to be 1. So a is 1/2. Equating the coefficients of t, we find right away that b has to be 4. And then equating the constant coefficients, b plus c has to equal 0. So c is the negative of b, which would be -4. So substituting these constants back into the general form for our particular solution, we find the particular solution would be a, which was 1/2 t e to the negative t, plus b, which was 4 times t, plus c, which is -4. And so for our general solution of this non-homogeneous equation, we take the sum of our homogeneous solution, which was c1 e to the negative t plus c2 cosine t plus c3 sine t, and then we add our particular solution, which is 1/2 t e to the negative t plus 4t minus 4. So in this first example, we see that the method of undetermined coefficients for higher order linear equations works the exact same way as for second order linear equations. We just have higher order derivatives to evaluate. So let's look at another one. In this next example, we have the same sort of problem. We are asked to find the general solution of this fourth order linear non-homogeneous equation with constant coefficients. And so again, our first step is to consider the corresponding homogeneous equation. The fourth derivative of y minus 4y double prime is equal to 0. And if we look for solutions of exponential form, y equals e to the rt, then r must satisfy the characteristic equation r to the fourth minus 4r squared is 0. So if I factor out r squared, I'm left with r squared minus 4. And then that quadratic can be factored as r plus 2 times r minus 2. So we find that we have roots of 0, which has multiplicity 2, -2, and +2. So our homogeneous solution has the general form c1 plus c2 times t plus c3 e to the negative 2t plus c4 e to the positive 2t. And now we need to find a particular solution. So when we look at this g of t function on the right-hand side of our equation, we see that it is the sum of a quadratic, or a second-degree polynomial, and a constant times e to the t. So for our particular solution, we might start by considering something of the same form. Let's take a general quadratic, at squared plus bt plus c. And then we could add a constant times e to the t. Now when we compare this with our homogeneous solution, we see that both a constant and a constant times t are part of the homogeneous solution because 0 was a double root of our characteristic equation. So the two terms in our particular solution, bt and c, would be solutions of the homogeneous equation. So we need to take this quadratic that we started with and multiply by t squared, since 0 was a double root. And that would give us at to the fourth plus bt cubed plus ct squared. And then I have a constant times e to the t, which was not part of the homogeneous solution. So this should now be the correct form. And to substitute this into our non-homogeneous equation, well, since it's a fourth order equation, we're going to need our first four derivatives. So for y prime, we would have 4a t cubed plus 3b t squared plus 2c t plus d e to the t. For the second derivative, we would have 12a t squared plus 6b t plus 2c plus d e to the t. For the third derivative, we would have 24a t to the first plus 6b plus d e to the t. And then lastly, for the fourth derivative, we have 24a plus d e to the t. So taking these expressions and substituting into our non-homogeneous equation, we have the fourth derivative of y, which would be 24a plus d e to the t, and then minus 4 times y double prime. So for negative 4 times y double prime, we have a negative 48a t squared minus 24b t minus 8c minus 4d e to the t. And we need this to equal our g of t function, which was t squared plus e to the t. So collecting like terms on the left-hand side, we have a negative 48a t squared minus 24b times t, then a constant of 24a minus 8c, and then minus 3d e to the t. And this has to equal our t squared plus e to the t power. So when we equate these coefficients, starting with the t squared terms, we have negative 48a has to be 1. So a is negative 1 over 48. Negative 24b has to be 0. So therefore b is 0. Our constant term, 24a minus 8c, has to equal 0. So that means c is equal to 3 times a. So c would be negative 3 over 48. And then lastly, equating the coefficient for the exponential, we have negative 3d is 1. So d is negative 1/3. So let's see what we have for our particular solution, y of t. We have a, which is negative 1 over 48, t to the fourth power, plus 0, t cubed, plus c, which is negative 3 over 48, t squared, plus d, which was a negative 1/3 e to the t. And so for our general solution of this non-homogeneous equation, we have our homogeneous solution, C1 plus C2t plus C3 e to the negative 2t plus C4 e to the positive 2t. And then we add our particular solution, which was the negative 1 over 48 t to the fourth minus 3 over 48 t squared minus 1/3 e to the t. Okay. So let us consider some other examples. For our next one, we have the same sort of question. We are asked to find the general solution of this fourth order linear non-homogeneous equation with constant coefficients. So again, we will start by considering the corresponding homogeneous equation. The fourth derivative of y plus 2y double prime plus y equals 0. And to solve this, we look for solutions of the form y equals e to the RT power, which gives us a characteristic equation of r to the fourth plus 2r squared plus 1 is 0. And this can be factored as r squared plus 1 quantity squared. So we find that our roots are plus or minus I with a multiplicity of 2. So for these repeated complex conjugate roots, our homogeneous solution would have the form C1 cosine t plus C2 sine t plus C3 times t cosine t plus C4 t sine t. And now we need to find our particular solution. So again, to use the method of undetermined coefficients, we look at this g of t function on our right-hand side, and we see that it is the sum of a constant and a constant times cosine of 2t. So for our particular solution, let us consider something of the same form. Let's say a constant a plus, since we had a constant times cosine of 2t, I have to consider both a constant times that cosine function and another constant times that sine function. In comparing this with the homogeneous solution, we see that none of these terms are already part of the homogeneous solution, so this should be the correct form for our particular solution. Now to substitute this into our non-homogeneous equation, since it's fourth order, again we need to find our first four derivatives. So starting with y prime, we would have a negative 2b sine of 2t plus 2c cosine of 2t. Then for the second derivative, we would have negative 4b cosine of 2t minus 4c sine of 2t. For the third derivative, we would have a positive 8b sine of 2t minus 8c cosine of 2t. And then lastly, for the fourth derivative, we have 16b cosine of 2t and plus 16c sine of 2t. So substituting these expressions into our non-homogeneous equation, we're looking for the fourth derivative plus 2 times y double prime plus y, and that needs to equal our g of t function, 3 plus cosine of 2t. And so let's see what we have when we substitute these terms into the left-hand side and collect like terms. So I'm looking at my fourth derivative, the second derivative, and the original function. So let's group the sine and cosine of 2t terms together. So starting with the sine terms, for y, the fourth derivative, plus 2 times y double prime, plus y, we are left with a total of 9c sine of 2t. Then grouping my cosine of 2t terms, for the fourth derivative, plus 2 times the second derivative, plus y, we have a total of 9b cosine of 2t. And then lastly, I have this constant term for y. So I have a plus a, and this has to equal my 3 plus cosine of 2t. So equating these coefficients, starting with the constants, we see right away that a has to be 3. Equating the coefficients for cosine, 9b has to be 1, and therefore b is 1/9. And equating the sine coefficients, we see 9c has to be 0, and therefore c is 0. So this means that our particular solution, capital Y, is given by a, which was 3, plus b, which was a 1/9 cosine of 2t, and then plus a 0 sine of 2t. And so finally, our general solution of this non-homogeneous equation is the sum of our homogeneous solution, c1 cosine t, plus c2 sine t, plus c3 t cosine t, plus c4 t sine t, plus our particular solution, which was 3 plus 1/9 cosine of 2t. So let's now consider an example of a non-homogeneous higher order equation paired with a set of initial conditions. So here we are asked to solve this initial value problem where we have a third order non-homogeneous linear equation with constant coefficients, and we have 3 initial conditions involving y, y prime or y double prime at time 0. So again, for a non-homogeneous equation, our first step is to consider the corresponding homogeneous equation. Y triple prime plus 4y prime equals 0. And to solve this, we could look for solutions of the form y equals e to the rt power, so that r is a root of the characteristic equation, r cubed plus 4r is 0. So factoring out an r leaves me with r squared plus 4 is 0. And so I find that my roots are 0 or plus or minus 2i. So my homogeneous solution has the form c1 plus c2 cosine of 2t plus c3 sine of 2t. And now we need to find a particular solution of our non-homogeneous equation. And when I look at my g of t function on the right-hand side, I see that it's just t, or a first-degree polynomial, or a linear polynomial. So we could consider a particular solution, capital Y, of that same general form. A linear polynomial, something like at plus b. But we see that since 0 was a root of our characteristic equation, a constant is already part of the homogeneous solution. So we need to take our first-degree polynomial for the particular solution and multiply by t to the first power, giving us at squared plus bt. And now none of these terms are part of our homogeneous solution. So from here, we need to find our first 3 derivatives to substitute into our non-homogeneous equation. And we find that our first derivative would be 2at plus b. Our second derivative is 2a. And so the third derivative is 0. So substituting into our non-homogeneous equation, we're looking at y triple prime plus 4y prime, which needs to equal g of t. And so substituting these expressions in, well, y triple prime was 0, so we just have 4 times y prime, which would be 8at plus 4b, and this needs to be equal to t. So equating our coefficients, we find 8a has to be 1, so a is 1/8, and 4b has to equal 0, so b is 0. And so we find that our particular solution, capital Y, is equal to a, which was 1/8 t squared, plus 0t. So our general solution, y of t, for this non-homogeneous equation would be our homogeneous solution, c1 plus c2 cosine of 2t plus c3 sine of 2t plus my particular solution, which was 1/8 t squared. So now to finish out the problem, I need to solve for my constants by making use of the initial conditions, which means that I need to find my first and second derivatives of this general solution. So let's take a look at y prime here. For y prime, we would have negative 2c2 sine of 2t plus 2c3 cosine of 2t plus 2/8 or 1/4 t. And then for my second derivative, y double prime, I would have a negative 4c2 cosine of 2t minus 4c3 sine of 2t plus 1/4. So let's now apply our initial conditions. Looking at y at 0, we're left with c1 plus c2, which we were told must be 0. Y prime at t equals 0 gives us 2c3, which we were told must be equal to 0. And then lastly, for our second derivative, y double prime at t equals 0, we're left with a negative 4c2 plus 1/4, which we were told must be equal to 1. So let's see what this gives us. Looking at my third equation, I could solve for c2. I find that negative 4c2 is equal to 1 minus 1/4, so 3/4. And then dividing through by negative 4, we find c2 is negative 3/16. From looking at my first equation, I could solve for c1 in terms of c2. c1 has to be the negative of c2, so that would be a positive 3/16. And from the second equation, it follows immediately that c3 is 0. So our solution of this initial value problem would be c1, which was 3/16, plus c2, which is negative 3/16, times cosine of 2t, plus c3, which was 0, sine 2t, and then plus my particular solution, which was a 1/8 t squared. So here we have the solution of that initial value problem. And so for our last couple of examples in this section, let us consider some examples of finding the correct form for a particular solution if we're using the method of undetermined coefficients. So here we are asked to find the correct form of our particular solution, but do not evaluate the constants. Don't worry about solving for the coefficients. So for part A of this example, we have a third-order linear non-homogeneous equation with constant coefficients. And so we start by considering the homogeneous equation. Y triple prime minus 2y double prime plus y prime is 0. And looking for solutions of the form y equals e to the rt, we obtain a characteristic equation of r cubed minus 2r squared plus r equals 0. So factoring out an r, I am left with r squared minus 2r plus 1. And that can be factored as r minus 1 quantity squared. So I find that my roots would be 0 and 1, which has multiplicity 2. So here our homogeneous solution would be of the form c1 plus c2 e to the t plus c3 t e to the t. And now to determine the form of our particular solution, capital Y, we would look at the general form of our g of t function. So here g of t is a cubic, or a third degree polynomial, plus a constant times e to the t. So we might start by considering a general cubic, at cubed, plus bt squared, plus ct plus d, and then add a constant times e to the t power. Now when we compare these terms with our homogeneous solution, we see that since 0 was a root of the characteristic equation, one of the terms in our homogeneous solution is a constant. So we need to take our third degree polynomial, which involved a constant d on the end, and multiply by t to the first power. And then we had r equals 1 was a double root of the characteristic equation. So our homogeneous solution also contains a constant times e to the t and a constant times t e to the t. So our last term for the particular solution, where we have a constant times e to the t, must be multiplied by t squared, since 1 was a double root. So this gives us a particular solution of the form a t to the fourth plus b t cubed plus ct squared plus dt plus e times t squared e to the t. And so let's look next at part B. In part B, we have a fourth order linear non-homogeneous equation with constant coefficients. So same approach to begin with. We can consider the homogeneous equation, the fourth derivative of y, minus y triple prime, minus y double prime, plus y prime is equal to 0. And if we're looking for solutions of the form e to the rt, then we obtain a characteristic equation of r to the fourth minus r cubed minus r squared plus r is equal to 0. And to solve this, I could factor by grouping some common terms together. From my first two terms, I could factor out an r squared, which would leave me with r squared minus r. And then from the last two terms, if I factor out a negative, I'm left with r squared minus r. So factoring out a common r squared minus r, I'm left with r squared minus 1. And then if I factor an r from the first of these factors, I'm left with an r minus 1. And then factoring my r squared plus 1, I have an r plus 1 times r minus 1. And so I find that I have roots of 0, negative 1, and 1, where 1 has multiplicity of 2. It was repeated. So for my homogeneous solution, I have C1 plus C2 times e to the negative t plus C3 e to the t plus C4 t e to the t. And now let's consider our particular solution, capital Y. So to determine the form of our particular solution, we're going to look at the form of this g of t function on the right-hand side. And we see that the first two terms are a quadratic polynomial or second-degree polynomial. And then plus I have a linear term or a first-degree polynomial times sine of t. So for our particular solution, we might start with the same general form. Let's take a general quadratic, at squared plus bt plus c. And then we could add a linear term, dt plus e, times our sine of t function. But since this involved sine, we have to include the same sort of term with a cosine. So we would also have some other linear function, say ft plus g, times cosine of t. In comparing these terms with our homogeneous solution, well, we didn't see any sine or cosine terms. However, since r equals 0 was a root of the characteristic equation, our homogeneous solution already contains a constant, c1. So for our particular solution, we have to take this quadratic term, which involved a general constant c, and multiply by a factor of t to the first. And this gives us our particular solution, y of t has the form a t cubed plus b t squared plus c t plus d t plus e sine of t plus ft plus g cosine of t. So we see in this last example that this method of undetermined coefficients can be generalized. And of course, the more terms that our g of t function contains, or the more complicated our g of t function, the more complicated the general form of our particular solution.